All right, how's it going, everybody? We are here on Thursday, January 28th. We're going to talk about section 6.5 today, the unit circle. This is going to be a super important topic. This is going to be kind of basically the way that you actually are going to learn all of your trig function values and remember them all semester. The unit circle is also going to help us visualize lots of properties of our six trigonometric functions that is going to make using our trig functions much more easy to do things like model real world problems, as is broadly the goal of this class. So we are going to learn some new things today, such as properties of our trigonometric functions. But when it comes to the unit circle itself, all that is it's sort of like an alternate geometric perspective from which to view the same things that we've been talking about for the last couple sections. So this is going to be an alternate perspective to view the topics that we've already been talking about this semester. So what our hope is today is that you are recalling things that you've previously seen, remembering some of our trig function values, stuff like that, but recognizing that the visualization of a circle rather than a triangle is perhaps a better way for us to actually think about how our trigonometric functions are really defined. So currently, our definition of our six trig functions is very directly tied to talking about right triangles, and specifically the ratios of their side lengths. We are going to retain this concept of the right triangle here, but we want to kind of recognize that, like, in the last section that we talked about applying our trig function to angles larger than 90 degrees, which already has broken our concept of right triangle only type stuff out there, right? Further, we've seen that we can apply our trig functions to any angle from 0 to 360 degrees, and even more than that with coterminal angles that allow us to find an angle within 0 to 360 that will have the same trig function values. So when we're talking things more like 0 to 360, that says to me that a circle sounds like it's something that should be relevant here rather than just right triangles. So in a sense today what we're going to do is we're going to sort of redefine all six of our trig functions in such a way that it still retains everything that we've already learned. Nothing's going to change. But by changing our definition, it will allow us to encompass further, like more ideas that agree with all of our old ideas, and then make it easier for us to take on new ideas associated with our trig functions here, right? It just makes sense to start talking about trig with right triangles. It's literally called trigonometry. Tri is trig. I mean, that's three. Tri is three. It's the study of three-sided shapes. That's literally what the definition of trigonometry is. But it's going to turn out that we're going to kind of actually find more value in visualizing this from a circles perspective rather than a triangles perspective, to help us see all the things we want to see. So, as with our very special 45, 45, 90 and 30, 60, 90 triangles, we know that we're only interested in the ratios of side lengths to study our trigonometric functions. The actual amount of size doesn't really matter as long as the appropriate ratios are maintained. Very, very similarly with our circle, all that's going to matter is that some ratios of lengths are maintained. The actual size of the circle that we're going to think of isn't going to matter. Our proportions are what matter. Just like when we talked about our triangles being big, triangles being small, that doesn't affect the values of sine, cosine, tangent of the angles associated with those. The ratios will be the same. Consequently, when we talk about the unit circle, unit meaning one, a single unit, meaning we're going to talk about a radius 1 circle, by far the simplest circle we could ever talk about, the nicest, easiest radius we could pick. We're picking it only because it's nice. We can do 100% of all this math with a radius 7 circle. It's just going to add in a bunch of additional inconvenience that we just don't need. So we're just saying, let's pick the nicest circle that we can ever pick. Radius 1 circle. A radius 1 circle is the unit circle. If somebody ever says to you in life, hey, can you draw a unit circle? They mean a circle with radius 1. That's just what the word unit means right there, one single unit. Last class, we looked at a general right triangle with side lengths that we labeled A, B, R in the plane. Let's do the exact same thing, but let's also put the unit circle on our diagram right here. All right, so last class, we drew something that looked like, we drew our grid, and I said that we've got some maybe angle of theta right there, and that we decided there was a right triangle out here that had like A and B and R to be those three side lengths right there, right? So for today, what we want to instead be doing is drawing a very, very similar picture, but instead there's also going to be a circle on our diagram right here. helping us see the 360 degrees of possible angle that could ever really be taken on, right? And again, we can rotate by more than 360 degrees, but we know that that will be coterminal with some angle that is between 0 and 360 degrees. So this is still representative of, in a sense, all of our possible terminal ends of any of our angle here. So here's the important thing about our triangle here that we're going to draw. This triangle is also sort of like an ABR triangle, right? This is like our A, this is like our B. We've opened some angle theta right here. And importantly, remember that R equals 1. That's our unit circle, right? So instead of literally using R, I'm putting the number 1 for that radius length because we're always going to think of this as the unit circle. It's always going to be the easiest thing for us to do, is to think of a circle of radius 1 for all this stuff. Very importantly, notice that now I actually know one of the locations on the circle according to my diagram right here. It seems that we've gone A units to the right of the origin and B units up. So that says to me that A comma B is actually a point on the circle that's sitting right there, right? Now, what my question to you would be are, what are sine and cosine in this drawing? I'm going to say for this drawing, hey, nice, good, good, good. It is good to always get those little trig refreshers out there. This is stuff that a lot of people take once and then forget a lot of and then need a lot of reminders. So my question is, in this diagram right here, what is the value of sine and cosine? If I compute sine of theta here, sine is opposite over hypotenuse, which is b over 1. That's literally the same thing as the height b. If I go to compute cosine of theta, cosine is adjacent over hypotenuse. That's a over 1. That's literally just a. It looks like what we've just discovered here is that when we describe our right triangles as being inscribed within a unit circle, that literally the width and height at which our terminal side intersects the circle at the point AB, A and B are the values of cosine and sine. Exactly. So this is telling me that AB, that point AB, equals cosine of theta, comma, sine of theta as an ordered pair point right there. So we're going to get those values right there in a second. And one of the questions that we want to ask is, how do we make sure that we memorize all of our trig values easily? And that's going to be one of our goals for today. So those trig function values you're talking about in chat there, we're going to go on down the whole list of them and say, how do we know for sure which one this one is? That's right there. One of the things that the unit circle does for me is it makes it a lot simpler for me to memorize the values that we're all expected to know. And what we just saw from this drawing right here, can I do this? Nope, got mad at me. The unit circle gives us kind of a new way for us to define our trig functions here. We can see that cosine and sine of theta are literally just the xy coordinates of any point that our terminal side of our angle hits the unit circle. All right, so I just said that in sort of a lumpy way right there. For any angle theta through which we've rotated, there is a terminal side to that angle. It's the ray where the angle ended relative to standard position, where the initial side is x-axis, terminal side is where we ended by opening up an amount of theta. This terminal side will intersect the unit circle at exactly the location xy that is described by the cosine of theta and the sine of theta. Where we hit the unit circle are cosine and sine of the angle with which we've opened. So this is nice. Like, we literally were dividing by 1 was all that happened with our ratio. That's why we picked the unit circle and not like the radius 7 circle, so that we get those really, really smooth ways to define it right there. All right. So before, when we were looking at just this general triangle right here, we were getting things like sine and cosine were like A over R, B over R for some general angle that's right there. And so I said that the cosine function was a measure of width. It wasn't actually the width, but it was describing to us something about the width. Sine, we said, was a measure of height. It wasn't exactly the height, but it was giving us a sense of measurement of the height. Our positives and negatives agreed with above and below, stuff like that. Well, now that we're in the unit circle, the cosine function of the angle literally is exactly the width that we have move to the left or right for that point that's on the perimeter of the unit circle, the sine function of the angle is literally the height at which that point exists that intersects the unit circle, right? Of the point of intersection of the terminal side of the angle and the unit circle. So when we talk about these things in terms of the unit circle, we now get to specify more. These aren't just a measure of the width and the height. It literally is exactly what the length and the width and the height is. Length is a very generic word. I should stick to width and to height right there. So cosine is always going to give us a sense of how far left and right is our point relative to the center if we've opened up a certain number of degrees or radians. Sine is going to say what is the height of our point on the unit circle if we've opened up some number of degrees or radians right there. Cosine is width, sine is height. That's never going to change right there. So that's one thing to burn into your brain right there. So, for example, identify the values of the 6 trig functions associated with the angle formed by the ray from the origin to the point -1/2 root 3 over 2 on the unit circle. So I'm going to draw my diagram here. You're going to draw a whole lot of unit circles this semester. I know that I'm going to the point -1/2. So I know this is radius 1, right? So this is at like -1 and this is at like +1 right there. So I know that I'm going to go out to -1/2. That's that x value of -1/2. It's halfway between 0 and -1. I'm also going to go up to positive root 3 over 2. And by the way, I do think that there's some like value in doing this real quick. Root 3 over 2. I'm going to go to my calculator real quick. And a very important thing that I want us all to be 100% confident in is that root 3 over 2 is larger than 1/2. I'm getting 0.866 about right here. Right? A number larger than 1/2 right there. And this is a positive number, so I know I'm going to go up by that amount. And it seems like, yeah, this location that we're landing at right there does seem to be much closer to this full height of what we know as 1, because that height of 1, it's a radius 1 circle, so it's only going 1 in every cardinal direction right there. So it seems like we're referring to whatever angle this guy's going to be right here. Right? Well, since we're on the unit circle, since I know that this point is -1/2 comma root 3 over 2, it must be the case that this is equal to cosine of theta and sine of theta, right? That's literally how we just defined these values to be a moment ago, that a location on the unit circle is equal to the outputs from the cosine function and the sine function when you evaluate them on the angle that you required to get to that point, right? So we rotated through this angle, we landed at this point. Therefore, the width is -1/2. That is the value of cosine. So I can say things like, and I'm just going to do these in the order I normally write them, sine of theta must be root 3 over 2. Cosine of theta must be -1/2. So where do we go from here? Well, we want to kind of remember that those are the 2 primary trig functions. Those are the 2 that we kind of need to know. All the rest of them just come from that. So things like, I should be able to say things like cosecant of theta, therefore, is the reciprocal, 2 over root 3, or 2 root 3 over 3. Cosine is going to give us the reciprocal for secant, which is going to be -2 over 1, which is just -2. I can combine these 2 together to give me tangent. I know that tangent is sine over cosine. And that's going to give me root 3 over 2 over -1 over 2. My divisions by 2 are going to cancel on top and bottom, leaving me with -√3, right? The negative is retained, the root 3 over 1 is just root 3. So there's my tangent value. And then to get cotangent, we just got to flip that, so I'm going to get -1 over root 3, also known as -√3 over 3, if you would multiply numerator and denominator by square root of 3 right there, right? So the point here is, if you know a point on the unit circle, that is literally the values of cosine theta and sine theta, and we can always use, in fact, even just one of these to find all of the others. We had 2 of them right here, but we're still just using a couple of them to get to all of the rest right there. Nice, good, got those ones right there, nice. So, this is easy when we're given a point that's on the unit circle right here, but what we really want help with is more like taking in the angle and spitting out all the cosine. Oh no, you got those right? Cosine is the -1/2. Sine is the root 3 over 2. Tangent is Oh, you're right. It looks like you've got some of your reciprocals wrong right there. And again, you got your 2 over square root of 3. That's a fine format for that guy right there for... Oh, okay. I see in chat right here, just the person that's suggesting some answers in chat, and I'm seeing that you've got like all the right concepts right here. Remember that we know that sine doesn't have a co, so its reciprocal partner is the one that does have a co. Cosine does have a co, so its reciprocal partner is the one that doesn't have a co. There's one co in each partner reciprocal pair right there. So it looks like you've just got those two switched right there. And then that also brings in a flip for your cotangent right there as well. So you're thinking the right thoughts right there. Just got to remember which functions are tied to which functions. And again, kind of my bigger deal here is that I care much, much more about sine and cosine than I care about secant and cosecant and stuff like that. So there is sort of a ranking of priority here with those, and sine and cosine are just the ones that matter the most right here because those are the ones that build all the rest of them. So, using the unit circle to help us memorize our special trig values. This is a big thing right here. I am 100% certain that every single person that goes to take Calculus 1 after this class, which this is what this is like a prerequisite for, every single calculus professor is going to expect that you know off the top of your head the exact values of all sorts of sine and cosine values for all of our special angles. 0, 30, 45, 60, 90, and then the other versions of those, right? So if we're at 90, 30 more is 120. If we're at 90, 45 more is 135. If we're at 90, 60 more is 150. And then 180, right? So there's all these special angles that are out there, and we should know all 6 of our trig functions for all of our special angles. We don't want to do a ton of work. Remember that our goal is to be as lazy as possible in this memorization, but still be able to produce anything that we want to be able to produce. So what I want to do is identify what's the least I can possibly get away with memorizing and still know everything, right? I'm not just memorizing a ton of stuff. So let's step over for 1 second and take a look at this, right? So here is what is a filled out full unit circle. And by the way, where I found this was I went to Google and I did a Google search for unit circle. And then I went to the images page and I saw about 1 billion different versions of this. It's everywhere. It's not hard to find. And so where'd it go? Come on, man. I was just looking at you 1 second ago. Oh, did I close it? Oh, I just minimized it. Okay, here we go. So here is our unit circle. So there's a lot on this thing. And what I want to convince you is that this is not that bad right here. That's our goal for today, is to convince ourselves that we've got this. Don't look at everything all at once. Let's look at this little piece by little piece right here. The first things that you should recognize right here are that the innermost ring of information is all of our angles in degrees. 0 degrees, 30, 45, 60, 90. Our first quadrant, kind of our most important quadrant right here. We can do similar angles out here, right? Go another 30 degrees to get to 120. From 90, another 45 gets us to 135. From 90, another 60 gets us to 150. And from 90, another 90 gets us to 180. And we just keep on doing that. 30 more, 45 more, 60 more. From 270, 30 more, 45 more, 60 more. We can also see all the radians. And while I've been, and on the one hand, shaking my fist at you that you need to learn all your radians, I've also been doing like everything in degrees so far. That's going to change, I promise. We'll start transitioning to thinking more in terms of radians here. But you can see, I mean, this is just like miles per hour, kilometers per hour on all of our cars, right? You look at one more than the other, but they're both on there. Importantly, all the locations on the unit circle are all the ones that you're going to be expected to know, but look at the values that we see. So excluding positives and negatives, what are all the values that you see, smallest to biggest? Well, I see that sometimes I'm sorry, I'm going to write one other thing over here. It just doesn't want me to write on this, and I'm debating about what I should... No, I'm not going to do this. So we want to remember that all of these xy locations on here are the same as the value of cosine theta comma sine of theta. So what that's saying to me is that every single one of these ordered pairs on the perimeter of this thing is a value of cosine, or it's a value of sine that we got from one of our special angles, meaning these are the only values that you need to know. The next thing for me to see are things like root 2 over 2 comma root 2 over 2. We know that sine and cosine are equal when the two angles are both 45 degrees, both side lengths are the same, and therefore cosine and sine are both the same. I'm seeing things like 1/2 and root 3 over 2, And then over here, I'm seeing root 3 over 2 and 1/2. And even when I go into my other quadrants, what things are you seeing? Those same three values. Here's a 1/2, root 3 over 2, and 2 root 2 over 2's, and then another 1/2, and a root 3 over 2, root 3 over 2, 1/2, root 2 over 2, root 2 over 2, 1/2, root 3 over 2. This is the same three values being repeated over and over and over and over and over again around this unit circle. It looks to me like there are literally just 5 numbers of interest showing up on this page right here. So don't look at this and say, oh crap. Look at this and say, that's weird. There's only 5 numbers that I have to know on here, right? The 5 numbers I'm seeing here are 0, in order from smallest to biggest, 0, 1/2, root 2 over 2, root 3 over 2, and 1. We're certainly going to tack some positives and negatives onto this thing as we go along. We'll deal with the positives and negatives kind of separately, right? So I don't need to worry about those. There are 5 numbers that showed up on the entire perimeter of the circle. You only have 5 numbers to decide from. Every time you're trying to evaluate the sine or the sine or cosine of any angle, you have 5 choices. And, like even better than that, 2 of the choices are easy and automatic. 0 and 1 are only if you're at like a 0, 90, 180, 270. Those are our axis angles. Those are really easy. So what it really comes down to is for the hard angles, you have literally 3 choices plus a consideration of positive or negative, and that's it. We don't have much to memorize right here. All right. So I want to. All right. Here's what I'm going to do. Is I just want to. Here's what I'm going to do. Zoom out a little bit. I'm gonna do this a stupid way. I just want to bring in a version of this into my Microsoft Word document so that I can write on a little bit right here. Do that and copy it, and then let's go back over to Word. And I just want to kind of draw some things on here. It's way too big, so let's make that way smaller. Keep going. Keep getting smaller. Come on, you jerk. There we go. Oh, thank you, Word. That's where I wanted it. Top of the next page. All right. Come on, you could. Okay, just be a jerk then. That's fine. So, or unit circle, whatever. I'll just plop it down right there so it's like in the notes and stuff. Remember that for all points. Okay, it doesn't want me to write anywhere near this thing, so I'm gonna be smart and not, and I'm gonna write. Okay. Now you're just screwing with me, Microsoft Word. Stop popping things up. I'm sorry I brought that picture in. I'll delete it if I need to. Holy buckets. Okay. Okay. So I'm going to convince you how little we need to actually memorize here. You need to know all 6 trig functions applied to every one of the angles in the unit circle. But of the 6 trig functions, 3 of them are just reciprocals of the other 3. All right, so one thing I know here is that, oh man, I mean, just give it to me. Goodness gracious. 1 over sine is cosecant. 1 over cosine is secant. 1 over tangent is cotangent. All right? So that's the first bullet point saying, well, technically you need to know 6, but really 3 of them just come from the other 3. So that's not really a thing. Also, of the primary 3, sine, cosine, and tangent, tangent's just a ratio of sine and cosine. So what these first 2 bullet points are telling us here is, really you just need to know sine and cosine. There's 6 trig functions, but if you knew 2 of them, you've got all 6. Secondly, of all angles that could possibly ever exist, we can use the concept of complementary angles to find an equivalent angle within 1 revolution that will have all the same trig function values as ours. So even if we're talking about the cosine of 1500 degrees, I could chop off the additional bonus revolutions that we've done and find a single angle that is within 0 to 360 that has the same trig values as all of ours right there. So when we got our complement or sorry, I got the wrong word right there, complementary, coterminal. That's not the right C word. Concept of coterminal angles to find an angle with equivalent trig functions within 0 to 360. Now that we're within 0 to 360, what we saw last class is we all know our first quadrant. We don't want to have to memorize our other 3 quadrants worth of stuff. So we came up with the idea of reference angles. Reference angles will take anything in 0 to 360 and say, listen, I know my one angle within just 0 to 90 that's going to have the same values as that. We'll need to decide about attacking on manually a positive or a negative to it, but all this really says to me now is this. The only angles that you really need to actually deal with, the only thing you need to memorize is just the sine and cosine values of just the angles in the first quadrant. And from that, we can figure out all trig functions associated with all angles, right? So our goal here is to do the least work we can do. The least work we can do is learn just sine and cosine for just quadrant 1, and then use our knowledge of reference angles, coterminal angles, reciprocal identities out here to get everything else that we want, right? Our goal is to think small to know big right there, right? We don't want to just memorize them out. So let's see how Tony remembers his trig function values out here. There's 3 kind of categories that I lump these into. First things first. On the axes, you're always going to get for sine and cosine 0, 1, or -1. Popping back over super quick to my unit circle, you can see that on the axis angles, 0, 90, 180, 270, 0 and 1, 0 and 1, 0 and -1, 0 and -1. Those are the only values that you're ever going to get for any sines and cosines. And let's talk through just the axis angles right now. We know that cosine is a measure of width. So at 0 degrees, all of our width is to the right, and so we get a total width of 1. At 90 degrees, there is no left or right action, and so we get a width of 0. At 180 degrees, all of our width is to the left 1 unit, and so we went 1 unit to the left, so we got -1. And finally, our vertical guy right here at 270, there is no width component, and so we have a 0 for our width component. The cosine is the first chunk. For the sine values, at 0 degrees, our point hasn't risen at all off of the x-axis. There's no height associated with this point, so we get a 0 for the sine value. When we're at 90 degrees, or at pi halves, our rotation results in our point having only height and no width. So all of it is in the height component here, and so we did move up 1 unit. That's our sine value. Our sine value for 180 is 0 because there's no height associated with that point, only width. And finally, our sine value at 270 is -1 because all of our action is straight down. So it's all the sine component, and it's in the downward direction, so we get a -1, right? So sines and cosines are kind of pretty easy right here for the 90, for the 0, for the axis angles out there. 0, 90, let's say 0, 90, 180, 270 out there, right? They're always going to be 0, 1, -1. And so maybe I can say, for our cosine we're going to get 1, 0, -1, and 0, right? Those are my 4 possible angles right there of 0, 90, 180, 270. And our cosine value will say we went 1 unit to the right, we went 0 units to the right if we're at 90, we went 1 unit to the left if we're at, oh shoot, sorry, I switched over and forgot to switch over. Okay, let me start this over again. So my weird little diagram right here that I have for cosine is saying, if we apply the cosine to the angle pointing to the right, we'll get 1 because we went 1 unit to the right. If we go 90 degrees, our cosine value is 0 because we didn't go left or right at all if we went vertically. If we went 180 degrees, then all of our action was to the left, so we went 1 unit to the left, and that's our cosine value. And if we went straight down 270 degrees, we'll get a cosine value of 0 because we didn't go left or right at all. Alternatively, for the sine, we should get sort of an inverted graph right here. Sine is measuring height. Right? Remember, this is width, and this is height. If we have gone 0 degrees of rotation, then that point has 0 units of height, and so we'll get a 0. If we've done 90 degrees of rotation, then we're pointing straight upwards. All of our components is positive height in the positive direction, so it's 1. Once we're all the way over to 180, our point again has no height on in the coordinate plane out there. So we're back down to 0 height at that location. And if we go 270 degrees, we can see that all of our height is downward direction right there. So we're going to get that -1 right there associated with sine of 270 right there. So remembering those is relatively easy. They're always 0, 1, and -1 if you're on any of the axis angles. And all you have to decide was how much left, right, up, or down was that. That's what sine and cosine are answering. And then when we're on the axis angles, it's all one or all the other. Notice that all of these have, like, a -1 is 280, cosine of 280. 0 is the sine of, or sorry, -1 is the cosine of 180. 0 is the sine of 180, right? One of the partner pairs is always 0 on an axis angle, because if you're on the axis, you either went left or right, or you went up or down. If you did both, then you're not on the axis anymore, right? So there's my axis angles. Next grouping here. I refer to these as the 45s. They're not all exactly 45-degree angles, but these are the ones that we are thinking go. So we've got 45 degrees. Adding 90 more to that, we get 135. Adding another 90 to that, we're going to get 225. And then adding another 90 to that, we're going to get 315. So these are all of the angles that have 45 as the reference angle. Well, I can pop back over to my unit circle and see the easy part about this one. On the unit circle, if I look at 45 degrees, I'm getting root 2 over 2 and root 2 over 2. If I go to 135, I'm getting negative root 2 over 2 and root 2 over 2. 225, root 2 over 2 and root 2 over 2, both negatives. 315, root 2 over 2 and root 2 over 2. It looks like the answer for both sine and cosine is root 2 over 2 every time for all of our 45 degrees out there, right? All the different versions of 45 degrees, all the angles that have 45 degrees as a reference angle. All right, so all sine and cosine values for all angles 45 degrees as the reference angle. Give plus or minus root 2 over 2 as the answer. How do you know if it's positive or negative? Just remember that we always get positive stuff from the first quadrant. In this quadrant, we went to the left and then up. In this quadrant, we went left and then down. And in this quadrant, we went right and then down, right? So that's all you need to know to get the sign that's going to be attached to that. So when people, if you ask me what's the cosine of 135 degrees, then I'm going to say, well, I know that cosine of 135 is one of my 45s. It's the 45-degree angle in the second quadrant. So I'm going to say it's root 2 over 2. And then I'm going to stop and I'm going to think to myself and I'm going to say, should it be positive or negative? I'm going to think about that as a totally separate concept. It's an after-the-fact thought for me. And then I'm going to say, well, if I was at cosine of 135, then I'm here, right? And notice how tiny my drawing is for myself. I know that cosine measures left-right amount. That one went to the left, so I stick a negative on it, and I'm done. There we go. Found my cosine of 135 right there. All the 45s are always going to give root 2 over 2. So those are all easy. There's 4 different of the 45s out there, my stupid angles right here. All 4 of those angles for sine and for cosine, you're going to get root 2 over 2 as your output. Your only real job is to stop and think to yourself, oh, it's cosine. So is it on the left side or the right side? Negative, positive. It's sine. Is it on the bottom or the top? Bottom's negative, top is positive right there. All you've got to artificially think about is attaching the positive or negative to it. Other than that, all the 45s are always going to be our root 2 over 2s. So let's stop and see where we're at so far. I told you that there are 5 outputs that you have to know. We've covered 0, 1, and root 2 over 2. There's only 2 outputs left, and there's only 2 groupings of angles left, the 30s and the 60s. Those seem to be tied to the 1/2s and the root 3s over 2s. Those are the ones that are They're not hard, but they're the hardest, I think, because these ones are sort of easy here. So I'll say, so the question is, then I can find sine by just rotating cosine by pi halves and reverse by negative pi halves? Yes, and we're going to talk about the symmetry associated with the negative pi halves right there. That'll be our last topic of today because we're going to talk about some of our features of these functions right here. But yes, cosine and sine, they follow each other by 90 degrees right here. I think that what you can see is, looking up top right here, if you take this diagram, this upper right diagram, and rotate the whole thing by 90 degrees, then you actually get the other diagram that's right here, right? So they follow behind each other. Cosine and sine are going to have motion that like follows one another, where one is right in front of or right behind of the other right there. Yep, they're a shift off from each other sort of. So the 30s and the 60s, these are my really big ones right here. Right? So what we know is that all of our cosines and sines of all of our 30, our 60, our 120, our 150, our our 330 degrees, if we've gone all the way around, all of those have reference angles that are 30 degrees or 60 degrees. And what we can see is out of the 5 outputs that we've discussed, 3 of them have been covered. The only 2 that are left are positive a half, or positive negative a half, and positive negative root 3 over 2. So here's how I think about these ones. And the way that I keep this straight in my head is only by remembering this phrase. The square root of 3 over 2 is larger than 1/2. And you should notice that that has to be true because 1 is like the square root of 1. Well, if you're taking the square root of a larger number in the numerator of a fraction, then the overall value of the fraction is larger. They're both divided by 2 right there, right? So 1/2 is 0.5. Root 3 over 2 is about 0.866. So all I remember is just root 3 over 2 is the bigger. So I'm going to do some examples for this one rather than kind of like give a description. And so things like sine of 60. How do I remember really what's going on with sine of 60? When I'm given sine of 60, I will draw my 60-degree angle right there. What I can see from my angle here is that the vertical component is larger. So what I can see here is when I draw my angle of 60 degrees, I can see the triangle that it forms. In the triangle, I can tell that when we open up by 60 degrees, that this leg, the height leg, is longer than the width leg. Therefore, I'm going to choose the larger of my 2 choices, root 3 over 2. Because I know that sine measures height. My height is longer than my width. My 2 choices are 1/2 and root 3 over 2, so I pick the larger of my 2 choices. If I was asking for the cosine of 60, I'd still be right here. Cosine measures width. I can tell here in this triangle that the width is small relative to the height, and therefore the cosine of 60 will be the smaller of my 2 choices. It'll be positive 1/2. If I were to instead talk about the cosine of 150 degrees, out of 150, I'm pointing the other way. If I go 150, I can tell that my width is long, but my height is not as long, right? For the 60-degree guy right here. Therefore, the cosine has to be the larger of the 2 options, root 3 over 2, and it'll be negative because it's to the left. And the sine of 150, the smaller of the 2, will have to be positive 1/2. It's the smaller of the 2 choices, and it's a positive amount. So all we have to know is that we're picking between 1/2 and root 3 over 2. If you can remember that every 30-60 angle, 30, 60, and all of its equivalents in the other quadrants, all the ones that have reference angles that are 30 or 60, for all of them, your answer for sine and for cosine is either 1/2 or root 3 over 2, with a positive or a negative. You have to decide that for yourself for the quadrant. But you can always just say, well, root 3 over 2 is the bigger one. So do I have more height or do I have more width when I do that angle? And you've got your answer. That's all I really do there to help me have that like memorized. That's right there, right? So the real important key then is remembering cosine is measuring width, sine is measuring height. You can judge visually that there is more height than width in the triangle that I just drew. So the sine of 60 has to be the larger of our two choices, root 3 over 2. Because it was an upward component, I left it as positive. If it would have been a downward component, I would have made it negative. If this was sine of negative 60, it'd still be that the height component's greater than the width component, but it would have been a downward angled one right here. And so I would have said negative root 3 over 2 for sine of negative 60 right there. Stuff like that, right? So these are sort of the three broad groups of angles that we have to know about. The axis angles, the 45s, and the 30s and 60s. The only outputs that we're ever going to get are 0, 1, root 2 over 2, 1/2, and root 3 over 2. And you'll have to decide, are they positive or negative, depending on up versus down, left versus right. All right, so by doing this, we have like kind of really, really little to know. Now, it's generally practical. I know a lot of people really like to just have their unit circle available for them, and that's like okay. It's not like I'm going to like tell you can't have a unit circle out when we're taking online classes and stuff like that. But also like there's a pretty big amount of value in you stopping and really convincing yourself rather than me try to convince you. You should convince yourself that this is a pretty manageable thing to have like fully memorized here, basically. Because it is. Because there's so little to know. Everything breaks down into just these three categories. And as long as we can visualize the geometry and remember that cosine measures width and that sine measures height, then this ends up being actually kind of pretty easy. You know that your choices are these 1/2, root 3 over 2. Root 2 over 2s always go with the 45s. There's not as much stuff going on as it seems like, is I think a good takeaway to see from this guy right here. So this definitely will require some practice on your part, but it's doable. This is not. I just feel like a lot of people, like when I teach, I don't know, when I'm in person and I actually get to see all of your lovely faces, I see a lot of like whites of the eyeballs when people do this, where they're like, oh my goodness, and it's like, take it easy. This is a real little bit, and you convincing yourself that this is just kind of a little bit of information matters. I don't expect you to just know this now. It will take a little bit of practice, but with a little bit of practice, this is easier than it ends up seeming when it's first presented here. So, and we'll do a little bit of that here today. So, one of the big motivations for transitioning into the unit circle definition of all of our trig functions is it really helps us visualize the properties of trig functions much, much easier than if we were only stuck talking about right triangles. What we want to know is a lot more about what sine and cosine do for us. We want to be able to do things like, by literally next class period, model the weather. Yeah, exactly. Every test in a month here, yeah. But it's not clear how we're going to do that yet. We want a little bit more information about these functions to see how do we apply these to real world scenarios here, right? So by identifying some of these properties of these functions, we will better understand how to graph these functions. And by graphing these functions, it's going to help us use these functions to model real world phenomena, which again, we're not taking this class for the fun of it. We're taking this class because it should be the case that these trigonometric functions define the things that we observe in the world, and that we want to be able to make predictions about those things that we see out there. And so that's going to be kind of our goal, and we're going to be able to do some pretty cool stuff within just a class period or two with this real world modeling here. But it's going to depend on our ability to identify a bunch of these properties. So what we're going to do today now, so this is sort of like a two-part day right here. Part one of today is the unit circle, which we kind of just sort of finished defining how we use it up above. Now we're going to talk about domain, range, and domain and range are one thing, period, and symmetry. And let's talk about those three properties of these trig functions, and that'll be sort of our second topic of the day here. So domain and range is a really important thing, and I know that probably about half the people taking this class already know the definition of domain and range, and half of them do not. And so let's state it right here. Domain and range are properties of functions that say what are you allowed to plug in and what are all the things that you might get out. It's the inputs and the outputs. And what we know is that not every function you're allowed to plug in any number, and there's lots of functions where there's numbers where you couldn't ever possibly get them out no matter what you plugged in. Right? So it's inputs and outputs is really the discussion that's happening here. So domain is the set of all possible inputs, x values, according to the way that I've written my expression there. And our range is the associated set of all possible outputs, or y values from our functions here. If we think about x is in and y is out, then this is just describing to us what are all the things that we might, that we're allowed to plug in, and if we plugged in all those things, what's all the stuff that we could ever get out? And it's going to be intervals of values out there, right? So I know that, and again, in this class, it's pretty typically the case that about half of all of us have taken algebra and half of us have not. So we want to talk through this. I'm hoping that about half of all of us for sure recognize this. And for the other half, I don't think this is too big of a stretch. It just might be something that you haven't quite seen before, right? So our goal is to name all of these for our 6 trig functions. That's what we want to do in a second. But let's do these with some algebra functions that we might be previously a little bit more familiar with here, right? Now remember that these are all like y equals f of x equals. This is like the function y equals x right here. This is a line. It has slope 1 and y-intercept of 0. And so graphically, a thing that's very helpful for me is that graphically I can see with this function, there's no like natural restriction to this, right? If I want to plug in a billion, then I plug in a billion, and what do I get out? Well, 1 billion again. So it seems like I can plug in anything I want for x because I'm not doing anything to it that would make anything weird happen. And everything I get out is just what I plug in. So the way that I might describe this is I would say that our domain here is going to be all real numbers. It's everything in the interval from negative infinity up to positive infinity. It's every single number. Another way to write this, by the way, this little double stick R stands for all real numbers. Right? And so if you're saying, no, you're allowed to plug anything into that function, then we can say this by saying any number from negative to positive infinity, or saying all real numbers, everything. This is the everything's allowed. Our range that's associated with this, and by the way, R here I'm using for range, is different than the double stick R. The double stick on here indicates it's a number set right there. Similarly here, we can see that this graph goes down forever and it goes up forever and it doesn't miss anything in between. So that also says to me negative infinity to positive infinity, or all real numbers, is also an acceptable range for this guy right here. Now, x squared is going to be a little bit different. So one question I might ask you is, what numbers are we allowed to square? What numbers does it make sense to square? And I usually like to think about groupings of numbers. Can I square fractions? Yes. Can I square square roots? Yes. Can I square positive numbers? Yes. Can I square 0? Yeah, 0 squared is 0. Can I square negative numbers? Well, yeah, negative 3 times negative 3, it's positive 9. What feature of this graph did I just describe by saying what I just said right there? It sounds to me, I was asking about domain right there, saying what am I allowed to plug in? And what I think I just decided is that our domain, here's what I'm going to do, is I'm going to switch back and forth just so there's a little bit of visual help right here. Right, so that's what our quadratic function looks like right there. My domain for this guy, what numbers am I allowed to plug in? What numbers am I allowed to square? I can plug in anything, but what types of numbers do you always get out when you square a number? If I square positive 3, I get 9, and if I square negative 3, I also get 9. You should be able to visually see in our graph that all of our outputs, all of our y values are 0 or larger. There's never a case that y equals x squared outputs a negative number. When you square a number, it becomes positive. So in this case, I might say things like 0 to infinity. Notice I placed a bracket on the 0 to indicate that 0 is included in the set. Parentheses indicate a number that's not included, and infinity is not really a number at all anyway, which is why it gets the parenthesis right there. But parentheses versus brackets, those are really the same thing as equal to or not equal to right here. So our other way to say this might be all of our y values are greater than or equal to 0. It's a description of all the y's that we might see over the course of using that function right there. We'll never see any that are less than 0. 0 is possible by squaring 0. All positives are possible by squaring whatever the square root of that number is. Right? Now, a little bit differently, it's the square root function right here. The square root function, if you know its graph, the graph is very helpful, but not all of us know the graph, right? But our definition of the square root function here says it only makes sense for us to take the square root of a positive number. So I might say here 0 to infinity, or x is greater than or equal to 0. And similarly for our range here, we can kind of see that this entire graph lives in the first quadrant where x's are positive and where y's are positive. So we're going to get matching domains and ranges here of positive numbers only, and 0 is okay. Square root of 0 is 0. Right? And remembering that domain is inputs, x values, range is outputs, y values, right there. Right? The way that the square root function is defined is you only take square roots positives, and you only get out square roots positives. A little bit later in your math career, we'll talk about taking square roots and negatives. It turns out it's actually a really practical thing to do, but it's not a real number. That is separating us from the real numbers. We're talking about real numbers here. And as far as the real numbers go, we've got our full answer right here. So looking at our last one, this one's a little bit different than the previous ones as well. Our 1 over x function, I think, has the graph that I expect the least number of people to recognize. It looks sort of something like this guy right here. And this graph is unfortunate because it's sort of got some properties that aren't obvious by first glance right here. But in talking about our domain and range, I think in this one the graph is actually less helpful. My question to you is, what type of numbers am I allowed to actually plug into this thing? Why are you spinning your wheel there? Word stopped and stuff. Can I plug in anything I want into this function? The one number that would ruin this for me is x being 0. There's no such thing as 1 over 0 right here. So for my domain here, I'm going to write this an easy way and I'm going to write this a hard way. My domain should be to say I can do 1 over any number but 0. It's literally all real numbers except for one of them. There's only one number that doesn't work. So I can either write this, the kind of hard way would be to say, get all the negatives out there, go up to 0, but don't include 0. So it's a parenthesis, not a bracket. That U stands for union. That says join that group with also the group from 0 to positive infinity, but again, not including 0. So this is us sort of like pinching out 0 right there. It's up against two parenthesis groups. So it's like 0's right in between right there, and it didn't get included into either of our two sort of halves right there. Now, that's kind of a bunch of notation that I'm not myself totally worried about. So I would say to you in this case, I would just say x is not equal to 0 right there. Just putting a line through your equal sign to say not equal to. I think that's our cleaner way of actually saying that guy right there. And our hardest one, I think, is the range of this function right here. A thing that's slightly difficult to see here is, are there any numbers we can't get out from this fraction? And I'm noticing I can get out big numbers. I can see it in my graph here. Notice that if x is like 0.1, 1 divided by 0.1 is like 10. So I can get large numbers for y by plugging in small numbers for x, and we do see that. Notice as our x value gets really close to 0, our y values are huge. And that actually goes, same true on the other side, right? Small negatives make huge negatives for y right there. But what's the one value that seems to be missing again? It seems like these two graphs are like avoiding these zeros right here. Notice that in any fraction, the numerator is describing the count and the bottom is describing the step size. Even if we make our step size really, really, really big, like make x 1 billion, we're going to only get 1 billionth, which is certainly a tiny number. But there's no x number large enough to actually make this straight up 0, right? 1 billionth is like saying out of a billion parts, you have one of them. But if you are guaranteed to always have one part out of some number of parts, you never have nothing. You always have something. We always have one part out of some number of parts. So in this case right here, I hope that at least by my word argument, you are convinced that there's no way for us to have nothing as an output because we always have one part out of X number of parts. We never have nothing. We've always got one of something. And it might be one of a very small amount, one out of trillions and trillions. It's still something. It's still a little bit bigger than 0 right there. So in any event, the purpose of this is to say, think in terms of domain and range. Domain and range is absolutely something I don't care about for algebra functions for you. It's something I absolutely do care about for trigonometric functions for you. We just did this exercise because I think these are functions that people are already comfortable with. We now want to think about these in terms of trigonometric functions where we're technically slightly less comfortable here. So let's see if we can identify what we think our domains and ranges are. And here's the other sticking point. With these ones, I'm kind of helping knowing my graph to visualize these. We're not talking graphs till next section. That's tomorrow's video right here. So like we don't get to use graphs here. So let's talk the domain of sine. I'm going to keep on rewriting the things I'm writing because I don't like the way I'm writing this here. So for the sine function, I am thinking of this as like a y equals sine of x. And my question to you is, what kinds of things can I get out, or sorry, what kind of things can I plug into the sine function? And we basically answered this last class. We know that in this case, x is like an angle because it's going to a sine function. And we saw last class, man, we can plug in any angle we want into this thing. If we've got extra revolutions, we chop them off with coterminal angles. If we're not in 0 to 90, we use reference angles to think about it being in 0 to 90. But we ultimately can do all of these. So our domain for the sine function is going to be negative infinity to infinity, or all real numbers. I don't care which notation you use. Whichever one you're already comfortable with, do that one. However, for the range of the sine function, we've seen all possible outputs here, right? We don't, there's nothing else that we can get. We know that we're stuck like on this unit circle, right? So if we come back up to think about all the outputs that we ever got from sine and cosine, we saw them all. 0, 1/2, root 2 over 2, root 3 over 2, 1, and then we got positives and negatives of those as well. So if I want to, I guess what I should do here is think about, since these are coming from our unit circle here, back to our unit circle, sine is measuring the height on the unit circle. Well, what's the lowest height and the highest height that we get? It looks like we go down to -1 at the lowest and +1 at the highest. We do actually achieve those values. Sine of pi halves is 1. Sine of 3 pi halves is -1, so they're included in there. But it doesn't seem like there's any way for us to get out like a sine of 7 or something like that. The reason why this isn't possible is because sine is always going to be opposite over hypotenuse. If we were going to get a number bigger than 1, that would mean that one of the legs of our triangle was longer than the hypotenuse. And it's a guarantee in every right triangle that the hypotenuse is always the longest leg. And so it's not possible for us to get a ratio larger than 1. That would say a leg was longer than a hypotenuse, and it's not physically possible in geometry. Like, you can't draw that. There isn't one that does that. So our range here is going to be -1 to 1. I'm using brackets instead of parentheses to include, to say -1 is an included value. You can get -1. I don't have really a smarter way to say this. I guess okay, that's not true. I could say -1 is less than or equal to y is less than or equal to 1. Our output values are stuck between -1 and 1 and could be equal to -1 and 1. So there's our first one, our domain and range. And we saw our answer in the unit circle and from last class period, basically. So cosine. Y equals cosine of x. Right? In this case right here, you should see we're getting the same thing. If we can take the sine of it, we can take the cosine of it. There's nothing exciting happening there. In fact, I said earlier, based on a good question in chat, all of our sine and cosine values are really just a rotation by 90 degrees of one another right there, a rotation and a flip. So anything that can go into one can go into the other. Very similarly, our cosine measures horizontal stuff, and we can go to the left one and to the right one, because we're stuck on the unit circle right here, right? So exactly the same answer is what we're going to get for this guy right here. Nothing different right there, right? Same thing, or -1 is less than or equal to y, is less than or equal to 1. Those are the not super exciting ones. Now let's do tangent. And tangent is ever so slightly more exciting. Oops. Oops. Man, I can't just write the thing I'm meaning to write right here. I want to think of these as x's and y's because I know that's where everybody's comfortability is with like inputs and outputs and stuff like that. So I think a really important thing for me to remember here is that this is sine of x over cosine of x, right? And so here's some things that I know. One thing that affects my domain is I want to say to myself, I know I'm never going to want to divide by 0. So one question I have is, what angle causes cosine to be 0? Which ones? Cosine measures width. The angles that result in no width are 90 degrees. And now we have negative width, negative, 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 270, back to no width. From 270, we're rotating through. We have positive width, positive width, positive width. All of our width is 1. And we're back around here to, 450 or whatever it is, or back to our 90 degrees right here, right? So it seems like these two vertical ones are where cosine is 0, right? It seems like that would cause us to divide by 0, and we don't want that to happen here. So it seems like our domain is exactly right there. So all of our cosine values, um, I'm going to say all x's except where cosine of x equals 0, which is where x equals, our first one is pi halves, that's vertical. Our next one is 3 pi halves, that's down. And then we could do another pi rotation, 5 pi halves. It also could have been the case that we could have gone the other direction. I could have thought of this as, instead of doing my positive direction of rotation, I could also think of doing a negative direction of rotation. We went negative pi halves, that would also be it. So the point is, starting from pi halves, if you do another integer multiple of pi, any of those are discluded. So x should not be equal to pi halves plus, and I'll say pi k, where k is an integer. Right? Those are all the infinite number, integer. Uh, there's an infinite number of times that cosine will be 0, right? Because we just rotate around forever and ever and ever. And it's 0, and then it's 0, and then it's 0, and it's 0, and it's 0. We're trying to account for the infinite number of points that we want to pick out of the domain right there, where we would divide by 0, and that's not cool. And so we're trying to describe it as succinctly as possible right here. So I think that this is like sort of our best way to describe our domain here, saying you can plug in anything you want as long as you don't make cosine of x 0, because that would cause us a division by 0 error right there. Cosine of x is 0 at all those locations. So those are all the ones we don't want as part of the domain of tangent. They're not one of the acceptable numbers for us to plug into tangent. Right? So let's keep going right here. The range with this one is a little bit less obvious, I think. And I mean, this one was pretty hard right here as well. So continuing on right here for our range. The thing I'm still seeing is I want to think about this as sine over cosine. So one of the things we saw before, one of our weird ranges a minute ago, was that we couldn't get out 1 or 0 from a fraction because we always had 1 on top. Well, over here, that's not the case. If we did 0 degrees, sine of 0 is 0, cosine of 0 is 1, because we're right here. We're getting 0 over 1, that's 0. So it seems like 0 is possible. As we rotate through these values right here, our sine is getting bigger and bigger, and our cosine is getting smaller and smaller. And so it seems like these tangent values are going to get huge, right? It seems like, for example, if we are at, I just want to do, for example, real quick here. Now, I'm going to have to go to my calculator to get this guy right here. But one of the things that I want to kind of identify with this one is that, like, I don't know what sine of 89 is, I don't know what cosine of 89 is, but I can picture that the sine value is almost 1, right? Cosine of 89, on the other hand, has almost no vertical component. It's almost 0. And so this is going to be a very big number, right? Because we're dividing by something that's very, very, very small. Ooh, close. Close right there. I'm going to go to my calculator and I'm going to do tangent of 89. I'm going to double check that I'm in math mode here, or degree mode. When I do tangent of 89, I'm getting 57.3 about. So you should notice here, tangent appears to be able to escape this boundary of -1 and 1 that cosine and sine have to live within. Because with tangent, since it's sine over cosine, we can be dividing by tiny cosine values. And when you divide by something tiny, you get things that are huge, right? So what we're going to end up seeing here for this guy is that we are going to get all real numbers for this output here. And my one question would be, how do we know that we get all negatives as well as all positives? And here's the thing I think that's worth thinking about real quick right here. Let's do another quadrant thing. I am looking for the positive or negative. When I say sine, the positive or negative sign that we're putting on the tangent function right here. Since tangent's sine over cosine, and we know that sine is just measuring height and cosine is just measuring width, we can think about that here, right? So in our first quadrant, tangent is sine over cosine, and both of those are positive. So we're going to get positive stuff in the first quadrant for tangent. In the second quadrant over here, my sine, right, it's sine over cosine. My heights are positive in the second quadrant, but my widths are negative in the second quadrant. And any positive number divided by a negative number is going to give me a negative value right there. So all the large positives that we get from being up here for tangent in the first quadrant, just on the other side of 90, we'll get those same large negatives if I did like 91 degrees in that example that we got right there, because then cosine would still be a tiny number close to zero, but it'd be a negative number close to zero. Now what are we going to get in the third quadrant? This is the exciting one. In the third quadrant, we've gone down, so sine is negative, and we've gone left, so sine is negative. And a negative divided by a negative, well, that's a positive. So we get positive things in the third quadrant here. And finally, in the fourth quadrant, we've gone down, so our sine is negative, but we've gone to the right, so our cosine is positive. And that's going to lead us to an overall a negative result for tangent right there. So the sine of tangent, we can think about what are the signs of sine and cosine in their respective quadrants. And so this at least helps convince me that whatever we get for positives, we're going to get that same stuff for negatives over here. This quadrant is a positive quadrant for tangent because it's negative for both sine and cosine, and those negatives are going to end up canceling right there. So that's why we know that we get all the positives and the negatives as well for tangent right there. So you should recognize that we did this the way that we do everything else. We talk sine and cosine first because they're the most important. We talk tangent second because it depends on sine and cosine. And then we talk about the other three by just flipping all the information that we'd previously seen, just taking some reciprocals out there, right? So let's do cosecant. Let me switch to blue so I keep my switch to blue. Okay. So let's talk cosecant. Is 1 over the sine of x. This is now our function of interest, 1 over sine of x. So I'm again going to say to you, is there anything we can't plug into this thing? And you should see that we're at risk of dividing by 0. We don't want anything where sine of x is 0. I know that our sine is measuring height. And when do we have 0 for our height? Well, at 0 degrees, 180 degrees, 360 degrees, 540 degrees, right? 720 degrees, all of our, or we could say this much more easily as 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. Those are all the angles that we don't ever end up with any height. So we're going to say, which x's don't we want? We don't want any of them that are just a constant multiple of pi, right? That's 0 times pi, 1 times pi, 2 times pi, 3 times pi. All those ones would give us no height. That would give us sine of x being 0. That would give us a division error. So this is the stuff that we can't have as in our domain. So we're saying x is not equal to any constant multiple of pi is acceptable. Any other value of x is acceptable right there. Again, k is an integer. So I think this is our like kind of good description right here. And by the way, I'm going to keep saying things like k is an integer because I want to kind of be more formal about it. But if you were to tell me x is not equal to pi k, I absolutely know that you mean k is an integer. So I'm good with that part right there if I'm asking you this question. And I will ask you some of these right here. I'm not going to beat you to death with the cosecants and secants and cotangents, but these are things that we should be able to reason through. Now, this one's a little weird as well. Now we know that sine, because sine has outputs between -1 and 1, that means we're only plugging in sort of small numbers into the denominator. And that should lead you to believe we're only going to get out large numbers from the overall fraction, because we're always dividing by a number that's at most as extreme as 1 or smaller. When we do things like 1 over 1/2, that gives us 2. Right? So I'm going to say sine of x is always going to give us outputs between -1 and 1. So 1 over sine of x, always dividing by small numbers, giving big numbers. All right. So this is saying things like if I divide 1 divided by 1/10, I get 10. Right? Now you should notice that the only way I could get like 1/2 out of this fraction is if I did like 1 over 2. But sine of x is never, ever, ever going to give us 2. Sine of x is always between -1 and 1. So it seems like what we can't get out is numbers between -1 and 1. And what we're always going to get out is numbers outside of -1 and 1 right here. This is a weirder one right here. This will be better once we see a graph of this, but this is a strange one right here. So here I think I can say that our y values then should be, all big stuff is fine all the way to 1. Notice that we can't, or sorry, to -1. Notice that we can get -1 because if sine of x is -1 at 270, then that's what cosecant is going to be, is also -1. 1 over -1 is -1. We're also going to union this up with 1 up to positive infinity because I can get out those big numbers as well. I just can't get, I'm missing that stuff in the middle, right? We're missing numbers between -1 and 1. Right? So for the sake of moving along here, I am hopeful that you guys are going to be down with the idea that secant is going to exactly follow our pattern for cosecant. The only difference is it's going to be dependent on the cosine function rather than the sine function. I'm going to try and just cruise through this one because I care slightly less about these. These also are a little bit harder, but it's also, we know that sine and cosine have so much in common. Secant, cosecant have so much in common. I'm basically just saying the same. The rationale is the same for all these guys, right? So for our domain for secant, it's just that we can't have x. You just can't have cosine of x being equal to 0. Now, this is one that we've already done, right? This is where we said we don't want cosine of x to be equal to 0 for that dividing by 0 purpose right there. It's the same exact thing. X can't be pi halves plus pi k right there. That would be what would cause us to divide by 0. Yep. So there's my good domain for that guy right there. Our range is going to have exactly the same type of stuff going on. I'm just going to say same as cosecant. Because it's still the case that cosine is between -1 and 1. So we're still only going to be able to get out big numbers because we're always dividing by small numbers. We can't ever get out small numbers because we're always, the small numbers are always in the denominator, not the numerator out there, right? So exact same reasoning for those guys right there. Let's wrap this up here and do our cotangent. And again, cotangent, we're just going to mimic exactly our ideas from tangent. We know this is the reciprocal, so instead of sine over cosine, it's cosine over sine. Again, our domain, our only issue with the domain is don't divide by 0. Can't have sine of x be equal to 0. We've already seen that. When did we not have sine of x being equal to 0? It looks like it was right here. Don't want sine of x to be 0. We excluded pi k. Sine is 0 when we're at 0. Pi, 2 pi, 3 pi, 4 pi. That's all where our height is 0 on the unit circle right there. So here I think we can say x is not equal to pi k. Constant multiples of pi. 0 pi, 1 pi, 2 pi. Those are all the places where we get a division by 0 issue here. And finally, for the range, it's going to follow, I'm just going to say same as cotangent, or sorry, same as tangent. All right, so again, a lot of the stuff that we're picking up here is really just saying, since we found out about one function, we already know the stuff therefore about other functions that are out there. And it's always going to be the case where I care less about these three guys right here, and I care much, much, much more about these three guys right here. Sine, cosine, tangent matter more than cosecant, cotangent. So these are the ones that you should expect for me to care more about your ability to discuss this domain range stuff here. And we're going to continue to explore these. Our very next section is going to be graphing a bunch of these functions. 6, 6, 6, 7, 6, 8 are going to be graphing these 6 functions. That's going to really, really help us to further explore exactly this. So even if this is a little tough for you right now, particularly this, you'll be helped a lot in the next couple sections with this material by seeing how we analyze the graphs of these guys. That'll be really helpful to kind of like buff out our knowledge here. This is a little bit tougher stuff, especially if you haven't talked domain range, notation. There's a lot of stuff going on there as well. So I don't think there's any more value in talking more domain and range right now. So I know we're kind of getting slightly long here. So I want to talk about kind of our last couple features here that we should be able to identify. These ones are going to be a lot easier than our domain and range. These aren't going to be like a bunch of work for us so much. So let's talk about this guy here. Period. What do we mean by period? Consider the point on the unit circle associated with theta. If we increase theta at a constant rate, what happens to the values of sine and cosine? Well, what we know is that since these are going to just be coterminal with other angles in 0 to 360, we expect to start with some cosine and sine values. Right at 0, we get cosine is 1 because it's all width. We get sine is 0 because there's no height. We're going to go 360 degrees, but by the time we get back around to 360, we're back in the same spot. Do it again to 720, back in the same spot. All the sine and cosine values that we get are repeating every full revolution. Every one revolution. Oh my gosh, I'm trying to write fast, and so I'm like skipping half the things I'm trying to write right here. Draw a repeat every one revolution, also known as every 360 degrees, also known as every 2 pi radians. Right? So these functions are going to repeat themselves. That's really practical for us to know. In general, we say that any function, and this is a stretch beyond a trigonometry class. There are non-trigonometric functions that also experience repetition. This broad class of functions is referred to as periodic. Yeah, and notation's just a thing where you just got to read it right there. You're totally right. It's like learning notation kind of sucks, but like when you read it for a purpose, it kind of helps you realize why we use certain notation that we do. So I agree. Notational refreshers are key always. So periodicity is repetitiveness. It's saying you're going to experience the exact same patterning over and over and over again. And it's just important to kind of recognize that there are functions other than trig functions that are periodic. And you'll hopefully get to explore some of those in some later math classes that are out there. So this is more of a general definition of periodic functions. Any function is considered periodic with a period of length p if there exists some value for p such that your function, when you apply it to theta, would be the exact same as the function if you applied it 1 period's worth later, right? And so that's going to be our 360 and our 2 pi for our sine and cosine. Right? So when we talk about sine and cosine, we can kind of, in a sense, visually see that these sine values are going to repeat every 2 pi, right? So what I'm really going to do right here is say, well, okay, I think what I want to do here is say that we get things like, we know that we're going to get positive signs and then negative signs and then positive signs and then, or sorry. I lied right there. We're going to get positives and positives, and then we're going to get negatives and negatives, and then we're back to the positives again. Right? So it's sort of like saying if you're going to start at 0, how long does it take for you to get back to evaluating the exact same whole cycle and not just the same value? Because notice that sine of 0, 0 and sine of 180 is 0. That doesn't mean we're repeating because our first half of all of our values from 0 to 180 gave us positives. Then our second grouping gave us negatives. But then we'd be back to getting the third grouping in positives again. And so that's going to say to me that in both these cases, here cosine is positive and then negative, and then negative, and then positive. It takes us 1 full cycle before we get back to fully repeating all the values. So for both of these two guys, our period is 2 pi, or 360 degrees. That's how long it takes for us to start repeating the values that we've already seen. The reason that I'm drawing our little positive negative quadrants right here is because tangent is different. We saw a second ago, I'm going to scroll back up for this one, that because tangent is sine over cosine, we can see our signs of tangent that it goes positive, negative for our 4 quadrants right here. I'm going to copy that down over here. What's going to happen here is that if we start at 0 degrees, we're going to experience every single positive value that tangent could ever take on. Then we're going to experience every single negative value that tangent could ever take on. Then tangent's going to be back down to 0 because tangent's sine over cosine, and sine of 180 is 0, just like sine of 0 is 0. So in only 180 degrees, we just experienced every single positive tangent value and every single negative tangent value. Now that we're down here, we're going to get all those same numbers again. The only difference is that when we did sine over cosine in the first quadrant, it was positive number divided by positive number to get some magnitude. Down here, this positive really came from negative divided by negative. So even though the sine and cosine were different in the third quadrant, this one's not, because the difference factor, the sign of positive negative, canceled, and we're left with just all of our positive stuff again. So we're going to see a full traversal again of all possible outputs from tangent are going to occur across the third and fourth quadrant. And then they're all going to occur again across the first and second, and then the third and the fourth, and then the first and the second, and then the third and the fourth. So in this guy right here, this only took us half of a revolution to experience all possible things before we started over again. Right? We didn't get the full periodicity here. Or we did, but it just only took half as long. So very importantly, we should know that sine and cosine are so closely related. Man, they have like all the same properties for the most part. And all the properties that are different in like in an easy to see shifted way. Tangent is inherently different here. Tangent does not take a full revolution to repeat everything. If you go 360 degrees, then you've passed through every single value of tangent twice already. Whereas sine and cosine, you've only passed through all of those values there at one time, where we start to actually see a repeat of the cycle again. So tangent cycle is half as long as sine and cosine cycle. So that's different there. All right. So that's kind of our the biggest takeaway right there. I'm hopeful that you are down with the fact that all of our cosecant, secant, cotangent information we just steal from their reciprocal partners. Since sine repeats every 2 pi, cosecant will repeat every 2 pi. Since cosine repeats every 2 pi, secant will repeat every 2 pi. Since tangent repeats every 1 pi, cotangent's going to repeat every 1 pi out there as well. We just snagged that information from that guy. So this is important though, and it's not hard to remember right here. Sine and cosine are going to repeat every full revolution. Tangent only takes a half a revolution to see everything and then to identically reproduce it on the bottom half of the quadrants down there. And so, as some very light examples right here, and these are relatively easy right here. All I'm thinking to myself is, using our definition of the periodic functions right here, we can say that this is like our sine of theta right here, and it should be that we should be able to rewrite this, or excuse me, this is like my sine of theta. Okay, all right. I know how I want to write this here. I'm going to write this as sine of, okay, I swear this one's going to be the one that I actually want this to look like right here. If I subtract off 360 from this guy, I'm left with 60 left over. And this looks exactly to me like our sine of theta plus p, which we were just defining as being equal to just sine of theta, which is equal to sine of 60, right? So this is just my like kind of roundabout long form way of saying, based on our definition of periodicity in periodic functions, we can hereby see that 420 is the same as 60 when it's being thrown into a sine and cosine function here, because 360 is one full revolution. This is the same idea as a coterminal angle right here ultimately. Now, by the way, let's do the exciting part of this guy right here. When I go to do this, I'm picturing for myself my 60 degrees. That's all I need to draw for my picture. My pictures never have anything more than this. I'm not asking you guys to draw complicated pictures. I am asking you to at least draw a picture like that for literally every angle. In this picture, what I can see is that my width is smaller and my height is longer. Since sine is measuring height, I know that I want to choose the larger of my two options for output here, and that's how I know I'm getting root 3 over 2. I can also see that my height is positive, so I'm going to leave this as a positive value for root 3 over 2 there, and that should be our value of sine of 420 degrees. Similarly, I can say that I know that tangent of 5 pi fourths, I can rewrite this as tangent of 1 pi fourth plus 4 pi fourths, which is just pi right there. This is my tangent of theta plus the period of tangent. Tangent's period is pi, so this is exactly like I've got it. According to our definition of periodicity, that should just then be the same thing as just tangent of theta without those extra rotations on there, which therefore to us is tangent of just pi fourths. I know that pi fourths is the same as my 45 degree. My 45 degree has both sine and cosine being root 2 over 2. Root 2 over 2 over root 2 over 2. That's the same number dividing by itself. That's going to be 1 right there. And we know that it's positive 1 because 45 degrees is in that first quadrant right there. So it's either positive over positive, or if we're being actually more appropriate about this, this right here, this is our pi fourths right here. That's our pi fourths. It's going to lead us to sine over cosine of positive over positive. Or if we did 5 pi fourths, it's going to be the same numbers, but it's going to be sine over cosine is going to give us negative over negative, which is also positive, right? So it doesn't even matter which quadrant you think of that in. And so that's how I know that that's going to be a positive result there, because the two different quadrants I can picture it in, it's either sine over cosine is positive over positive, giving positive, or it's sine over cosine is negative over negative, also giving positive. So it seems like tangent is positive here, and tangent is negative here, because in the second and fourth quadrants, one of the two trig functions is negative and one of the two is positive. So their ratio is going to be negative. And again, I know that this is associated with my 45 degrees, so this is going to be like our root 2 over 2 over root 2 over 2 is what I'm getting here for my sine over cosine. Right. So this periodicity definition is in a sense an alternate way to think about coterminal angles, but you should see for tangent, since it only takes 1 pi rather than 2 pi, so it's a little bit different right there maybe for tangent. But in any event, we can still do this evaluation here thinking about the periodicity of these functions, that we know they're going to repeat every certain number of units. Okay, last topic. This one will be quick right here, just like periodicity was. Symmetry. We've seen that sometimes two different angles can have the same trig function values. When can we expect this to happen? Oh, okay. So have good. You're mentioning an important thing right here. So I do want to back up and mention what you just mentioned right there. When I tell you that I want to know the tangent of 5 pi fourths or the tangent of pi fourths, both of those are going to be 1, because it's two numbers of the same magnitude that are both positive divided by each other to give 1, or two numbers of the same magnitude that are both negative divided by each other, giving us 1. However, if I tell you that I took the tangent of an angle and I got out 1, you should realize that you're not sure which of these two angles I gave. There's two possible answers right there. That's a beast that we're going to tackle in about 4 or 5 sections out there. That'll be our beginning of chapter 7, and that's really important, that kind of ambiguity about going backwards the other direction. It's not as obvious what we're getting anymore if we try and reverse this process, and that's important, but we're not going to open that can of worms today. But that's a good call right there, that we can't go backwards the same way as we can go forwards here. If I said to you tangent of theta equals 1, what's theta? We need a better definition to kind of figure out the backwards version of that guy. We'll get there. Okay, last topic, symmetry right here. I just want to draw for you two pictures and for you to say, yeah, I can see that those things are going to be the same like that. And that's what we're going to call our symmetry conversation here for the day. So we've seen that sometimes two different angles can have the same trig function values. When can we expect this to happen? Let's look at two sets of symmetries here. So here's the thing I'm thinking. I know that since cosine is measuring width, you should notice that, for example, if I open up by positive 30 degrees, my width is the same as if I opened up by negative 30 degrees, right? If I did up 30 versus down 30, my x component is still the same in both of those cases there, right? Now my y component had up versus down. The y component's different. The sine is different, but the cosine should be the same. Very, very similarly, if you're thinking about the height of an angle, if I were to go out like 80 degrees here, then I have some height component. The sine is measuring the height. The sine of theta is the height. Well, instead of going 80 degrees, perhaps I could go 100 degrees. Well, the sine, I've still got the same exact height on my point because it was 10 degrees past 90, and it was 10 degrees before 90 right there. And those seem to be symmetric height-wise on the other side of this angle right here. And so it seems like there are some special angles symmetric relative to 0 and symmetric relative to 90, and therefore symmetric relative to 180 and 270, that we can make some claims that some of these things are going to be the same. So I'm going to draw two diagrams here. All right, now, my diagram drawing here is not terrible, but it's not perfect either, right? So here I'm thinking about the two angles of positive theta and negative theta as I've drawn them right here. Right? I wish that my points were perfectly vertical of each other because that should be what's happening if you open the exact same amount of angle in the positive direction versus in the negative direction right there. And what I can see in this diagram here is it looks like the cosines of these are the same because the widths are the same. So that says to me, for all time, anytime I ask you what's the cosine of a negative angle, you can literally ignore the negative because the width will still give us the same, it'll still give us the same width description regardless of which of the two directions you opened up in, right? So I guess I'm sort of picturing like, instead of just doing your positive angle, like do them both and see that your x component is always going to match regardless of how much rotation you do right there. The heights are almost the same, but they're the opposite sign. When I say sign, I mean positive or negative. Heights are same amount, but different positive, negative right there. So this says to me that the sine of negative theta, right? If I found the height associated with going down, it should be the negative of the height as if we went up. So this is sort of saying to you, if I ever ask you to compute the sine of a negative angle, it's algebraically appropriate here, trigonometrically appropriate, for you to literally take the negative that's on the inside of sine and just pull it to the outside, and that will actually be the same thing. That's a legit move right there. And we can kind of just graphically just see it right here with these guys. So these two statements right here, that cosine of theta is always equal to cosine of negative theta, and that sine of negative theta is the negative of sine theta, those are true for all angles, which is really convenient for us. Now, some other things we want to see are what's up with, for example, so notice here, what we're trying to describe is what happens if we do a negative angle. How does it relate to a positive angle? So let's ask ourselves, what's up with tangent of negative theta? Well, this should be sine of negative theta over cosine of negative theta. Well, we just determined how to evaluate both of these. Cosine of negative theta is straight up equal to cosine of positive theta always. Sine of negative theta is the same as negative sine of positive theta. So it looks like this is going to give me negative tangent of theta. So I just did a little bit of math right there to kind of determine that. And finally, I'm hoping you're convinced that we get these same symmetry arguments for secant, cosecant, cotangent. I'm not even going to write them because I'm not going to so much care about those guys right there. But this is a really, really important set of symmetries right there. I guess I didn't mean to say that we're going to, let's look at symmetric angles. That's, I think, all I was really trying to say right there. So our three very, very important symmetry relationships that we're seeing here. I guess well, those are the ones that we already saw. In any event, from these diagrams, we can see that cosine of negative theta, it just eats the negative. Sine of negative theta pops out the negative. And since tangent is formed by sine over cosine, it also pops out the negative. And these are just really practical things for seeing that some quantities are the exact same as some other quantities out there. If you're ever looking to evaluate sines, cosines, tangents of negative angles, recognize that you can sort of handle the negative up front with this idea of symmetry that we've got in this diagram right here. There was some other things that I was going to say about kind of doing a similar idea right up here, where we could talk about this angle of theta and then this other angle over here of 180 minus theta. And we can make some very, very, very similar statements right here. That looks like in this case, our sines are equal. And by the way, have good. I think these are ones that you were maybe trying to tell me about last video right here. It was pi minus 180. Or sorry, pi minus theta or something is equivalent right there. We can see here that our cosine of theta looks like it's the negative of cosine of 180 minus theta. And our tangents here is again going to be negative, but that's because the negative is getting popped out from our cosine term, not from our sine term. All right, so slightly lesser used, but also other symmetries. So I'm just going to label this other symmetry. Right. And kind of where I'm measuring this, by the way, is notice that the way that I measured this is this 180 minus theta. This is saying, step one, do 180 degrees of rotation to get to here. Then undo theta degrees of rotation. And so that's where we're getting that symmetry from, that this must be the same like kind of angle as this one. They have the same reference angles. One said start at 0 and go in the positive theta direction. The other one said go to 180 and go backwards by theta. And so that's why those are perfectly symmetric angles that are right there. And we can again identify some of those relationships with symmetries that we see right there. So these are kind of our symmetries that we want to know about associated with positive and negative relationships with angles. And again, we're going to be able to visualize everything that we talked about today in graphs over the next 3 sections. So 6.6, 6.7, 6.8 is all graphs. And then in chapter 7, when we start chapter 7, that's when we're going to come back to the fact that this doesn't seem like a problem that we can work backwards from. Here, I gave you the input of 5/4. We determined the output of 1. But if I ask this question backwards, saying I took the tangent of something and got 1, what did we take the tangent of? It seems like there's 2 good answers right here, and in fact, infinitely more. So the backwards version, that's going to be weird to answer, and that's what we're going to start chapter 7 with, which is 3 more sections from now. Yes, and exactly. So you were saying you want to do theta minus 180, and so anytime I see this like addition, subtraction of angles, like literally do it as a step-by-step motion process rather than as trying to like visualize it all at once. When I see 180 minus theta, that says to me do 2 actions. Action 1, rotate by 180. Action 2, rotate by negative theta. And it's hopefully pretty convincing that that's this equal but opposite thing as just going from 0 just to positive theta right there. 180 minus theta is sort of like a bad quantity. It's like, think of that as 2 steps rather than as 1 amount. I think it's good to think of angles as like an action rather than an amount. It's an action of rotation. I think that helps me. I feel like I got things like that wrong for like ever, exactly like you're saying of like switching them and being like, well, I don't see why that's different. And like, and then it was one of those things where as soon as I saw it, I was like, well, of course that's the way that it should be. And so just think of 180 minus theta as a 2-step process rather than as one quantity. And I think it makes it easier to visualize why you're getting the thing you're getting right there. Okay, so kind of a lot of stuff today, but again, really reinforcing stuff that we've already learned, as well as setting ourselves up for a bunch of the graphical stuff that we're about to see in the next section, stuff like that. So your job is to know the unit circle. Your job is to for sure know the domain and range of at least sine and cosine, definitely tangent, less so the other three. You definitely need to know the period of sine, cosine, and tangent, and you get the other three for free. You're gonna want to know about our identities here because these are gonna make simplifications much, much, much nicer for us in the future. We're gonna get some grosser and grosser and grosser trig expressions as time goes on, and the more of these types of simplifications and modifications that you can do, the easier it will be for you to write big, gross trig stuff as little, small, easy things that have simplified nicely. So knowing these and at least being comfortable using them, even if you have to look them up, is really important right here. So I think it's a good idea to sort of like make a catalog of these things right here, so that you can do a quick lookup for these, because there's a lot of stuff that we've kind of brought in where if you had to memorize all this, it's almost too much. So think about reference knowledge for these and having like a smart organized sheet that kind of keeps all these identities and formulas for us. I think is a very practical thing that you can do here. And so, yes, have good. I'm going to answer your question in 1 second. I'm just going to say I'm going to wrap this up right here. Yeah, so have good. These are part of a college course that I'm teaching. I'm just doing them live on Twitch so that anybody that wants to watch them live can. I record all these videos so that I can post them so that all the rest of my students can see them after the fact, which is why they're attached to my YouTube page here. But yeah, in general, these videos will always be up on my Twitch page for 2 weeks after the recording, at which point Twitch will delete them since I'm not a Twitch partner. But yeah, so this is for a college course here, and I've got all my students watching these videos mostly after the fact, but I always figure in case anybody does want to follow along live, and since I do always appreciate having commentary in the chat over here, it's nicer for me to do these live and feel like I have an audience than just to record a video. And I wish we were in person instead of teaching online. So it's always good to have somebody here make me feel like I'm being watched. I feel like that's how I'm a better professor. So yeah, it's good to have you here, and Kina as well. Cool. And so that's for today. We're going to hit graphs of sine and cosine at 2 o'clock tomorrow. Um, nice. Cool. Well, yeah, I'm glad you've been joining us. So continue doing that. And we'll pick up with section 6.6 with some graphs tomorrow. I hope Desmos is your friend, and we'll look at a bunch of features of sine and cosine graphs only tomorrow. We'll look at our harder graphs later. So, hey, Inikdom1, thank you very much for being here. Yeah, refresher for this stuff is always key. I find that a lot of people learn trig and then it's a very sort of a forgotten thing, and refreshers for this is usually a flood for lots of people of stuff coming back to them. So good. Glad to have all you guys here. Thanks for being here, everybody. I'll see you hopefully tomorrow for our section 6.6 stuff. Have a good one.